the AI for wind energy challenge. Very excited to be here because wind energy engineers and academics have been trying to solve this problem for over 20 years. And we together are now going to show a path to a solution based on AI. And we do that as Tarucca and Fruit Punch AI together. And what is this problem? The problem is how do we detect remotely if and when a wind turbine blade needs repair? And why is that important? Is because if you can make that detection, we can increase the lifespan of the blade and enable recycling. We can lower the cost of wind energy, and we can make it practically possible with limited available manpower to maintain those 10,000 of wind turbines that are out there at sea. Without having a good solution for this, practically, this will not be possible. And what we have to realize is, say, to reach the EU climate goal by 2050 and to have it 100% CO2-free energy production, wind energy has to be 50% of all Europe's electricity production by then. And which means that we probably need about over 50,000 wind turbines more offshore than we have at this moment, which is a 22-fold increase in wind power capacity. The problem is that the wind energy industry is suffering from blades damage. And these blades, they get longer and longer. At this moment, the longest blades are as long as a football field. And what you have to realize is that the tip of those very long blades, they race around with the speed of a Formula 1 race car, close to 300 kilometers per hour. 47% of the offshore wind turbine blades require maintenance. And there are several causes for this maintenance or for this damage. We won't go into that now. But at this moment, the best way that is there is to periodically visually inspect those blades. And this can be done by manually, by people climbing up in the turbines, or it can be done by drones, by looking at it, or by looking at it with telescopes. The problem with that approach, as it is used at this moment, is that you don't monitor inside the blade to see if there is any damage inside the blade, and it's not scalable for frequent offshore checks. To have a predictive condition monitoring of wind turbine blades, a solution needs to be scalable, so it needs to be an automated approach. It needs to be suitable for both new and existing wind turbines, which means is that if it is based on sensors, you want to install those sensors not too far away from the root of the blade. And it needs to be reliable, so you need to limit your false positives. Eventually, algorithms are needed to define which blade is damaged, what is the type of damage, where inside the blade is the damage, how large or serious is the damage, and how fast is the damage developing, and when does the damage then eventually need to be repaired. In this challenge, we will focus more on the ones where there is the red question mark behind it, which blade is damaged, and how large or serious is the damage. That's what we're focusing on. Now, there is two obstacles here, and that is, let's say, later we will come back on the data set, but we're looking at a data set with sensors from all over the blade. But in practice, we will only be install retrofitting sensors and blades in the first 1/3 of the blade, if you measure from the root of the blade. So we really would like to see the signal that we can get out of the sensors from the first 1/3. The other complicating factor here is that in this data that comes out of the wind turbine blades, there is an enormous amount of noise. Because let's say the wind is varying all the time, the direction that the wind turbine is, the speed of the blades, the wind gusts. So there are a lot of variables in here besides, say, the damage in the blade, yes or no. Just a little bit background of us. As Tarucca, we are a deep tech startup at the high tech campus here in Eindhoven. We really believe in the power of innovation to deliver or to make the world more sustainable. And we are working on a solution, say, that addresses this problem so that we can, 365 days per year, we can monitor the condition of wind turbine blades. We use for that the latest photonic chip sensors, AI software, therefore we work with Fruit Punch here, and we really like the approach of crowdsourcing. In the end, the technological principle that this is based on is that there will be an invisible shift in the modal shapes of the natural frequencies between blades that are new and blades that are damaged. In the end, we will have a total system here with the photonic chips, an interrogators, computers, a customer user interface. But very important, and without that it is not possible, is to have the AI algorithms that would then run in the cloud. What we have here is an absolutely unique data set of the type that is normally kept secret. This data set has been used once or twice before by other researchers, but normally this type of data from a wind turbine with sensors in the wind turbine with an indication if the blade is damaged, normally this type of data is not available for the public. This is an essential first step. This Fruit Punch AI for Wind Energy Challenge, because what it shows is further proof that with AI, based on this sensor type of data, this decade-old problem can finally be solved. After this, we will do a field test with the latest photonic chip sensors and a real wind turbine. Then further data analysis and algorithm development will be needed. And in the end, this will all lead to collaboration with a large wind park for a solution feedback loop. But all those type of things to get to this final solution will not be possible if we don't first show here with this challenge, say, what we actually can do. Therefore, it's so essential. Why then this challenge for wind energy? First is to get that proof that with AI we can do this. Two is to also show towards the industry that is in generally quite closed, that an open approach, a collaborative approach, a crowdsourcing approach actually can give results. So we want to give a clear message to the industry that this type of approaches are very good for the industry. And in the end, of course, we do this because we want to make our world more greener and we want to create more sustainable energy.
So, and now I will get into more the nitty technical details of the data, because as you know, as data scientists, it's really important to know the source, the amount of data, and also the type. So we have two data sets for you guys to work with. The first week we start with dataset A, which is especially in a lab environment. And the reason we start with this one is because we have now a controlled environment where the temperature and all other conditions are locked. So it's very more easy to get to know how to work with the data. And what we see here on the right at A, that's a small wind turbine blade in a lab environment in Switzerland, in Zurich, which is both tested under healthy and damaged states. And this blade comes actually from a Spanish manufacturer who had provided it, and all the experiments were done by the technical university there. And on the rest of the picture, you see B, the settings which were used to control the climate room, and C is a shaker, which has been added to the end of the blade to excite the blade under certain frequencies. Under D and E, we see some sensors that have been added, F, temperature sensors, and G and H, you see 3 different types of cracks that have been added to the blade. So then we have the second data set called dataset B, which is actually a field test, which we have the data from, as Hans already told. And this field test has been conducted in 2014, where a prototype of such a system was installed on an operating wind turbine. It was actually an older model that they use right now, because this is a Vestas V27, and the 27 means 27-meter rotor diameter. And to compare it to the ones that are now in use, those are like around 100 meters. And why this is important details is because a rule of thumb, how longer your blade diameter gets, how less stiff they get. So what we have here, the data set, it's quite nice, but we have to take that into account, because this complexity in the future for the current modern wind turbines is an important factor as well. But this one is provided by some company for sensor equipment. And this guy, and we will talk about this later, will also work together for a masterclass, but I will get into the data later. So the amount of data available, if you look then at the data set A, the first one, we have a lot of data of it. We have actually 44 runs per case. And what is a case? It's actually a specific length of crack on a certain location. And there were 3 different locations, which A, B, and C are actually an added mass on the blade to also simulate how ice formation would be, but that's not the focus of this challenge. But the other ones, D till L, are different combinations of crack lengths. And R is a reference case, and there was one of an undamaged blade state. And as you see, for every case, you have this range of temperature points from -15 till 40 degrees. So a lot of data, I think around 90 gigabyte available to work with. And below you see, for example, case J. That's one of the last cases, the more critical ones. Their crack 1 has been grown to 15 centimeters, and which does not mean that crack 2 and 3 are non-existent, but they are still 10 centimeters. So every case is a grown out crack. Then we have the second data set, B, and that one is not categorized because it's wind turbine in operation. So the temperature is dependent on what the temperature will be in the field and also the wind conditions as well. But for the undamaged blade state, we have a lot of runs, more than 3,000 runs available. And for every crack that comes after it, the numbers are defined below. But the nice thing about this is we also have a lot of information available about the repaired blade state, which is nice because we can compare it to an undamaged blade state, because this one can also different as well. And we categorize this into different 5 folders, which also already have the state names, so you can play around with that. Then what kind of type is the data? So for the first one, the lab test, that the data is available both in time and frequency domain. So the top figure here, you see all the data in frequency domain. The red ones are actually acceleration measurements, and that's different from the strain measurements in yellow. Then you see the difference between A, B, and C, D. And the top figures, those are actually sine excitations. And the below figures are white noise. And this is also part of the 44 runs that I just told you a few slides before. And below you see, at the below figure, you see a power density spectrum. And what is actually nice about this, you see R, C, and L. And R plus 25 means the reference blade state at 25 degrees. Then we have C, that's the ice mass, and L is a severe case of damage. And the difference between A, B, and C, D is actually that A, B are acceleration sensor data, and C and D are strain sensor data. And you see 5 gray bars actually, and what these are different modal shapes, and you will work a lot with modal shapes because it tells something about the characteristic of the blade. And what I want to say about this one is that the first fundamental modes on the left, you see 1, 2, 3 on the left, and then 4, 5 at the end. The first 3 say less about the green line than the more later modes. And the reason is that the first modes, they only say something about the flap-wise movement of the blade. That means like in flap-wise direction, while the more higher modes, they also count a bit of torsional direction as well. And you see, for example, at C, that the difference between the blue line and green line becomes bigger. So also more damage resolution is available in this kind of information, which makes it perhaps interesting to take that a bit more into account. Then we have the type of data coming from the field test. There are 2 types of data of the field test. There's vibration data of the sensors on the blade, but there's also metadata consisting out of weather and operational conditions. And that weather data comes from a wind station, like a temperature station, 200 meters located from the blade. So it's really close. And comparing, so the vibration data itself, that consists of 30 seconds time history of every time kind of hammer ticks on the blade. And that signal, that history is available. So you have information available that correlates to the specific vibration together with operational and environmental conditions. And what we see below here, because it looks a bit disordered, it can be confusing. The top figure, we see B, an extraction of the data that's around the time the actuator hit on the blade. So that part is used for further analysis, and the rest is a bit of more irrelevant noise. And then the figure below, we see a lot of things, but actually the y-axis is also acceleration, and the horizontal axis is the amount of samples. And I put this in here because you see the amount of metadata available. You see, for example, the wind direction, and you see the temperature, but also power and pitch. So this all corresponds to the vibration data. Okay, and on the right, you see a sample actually of how this data is structured. You see at the data file name, you see that, for example, we are now looking at run 301, and this one was conducted at 10 December 2014 in the morning. What is also shown here is that the weather station is named, so V27HO blah, 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 blah. And what is further noted is that you can see the RPM, which is around 43 rounds per minute, and also the position of the blade, and that's the last one, S phase, 291 degrees. And you see also here that the pitch, so the pitch is around, if I get it correctly, around 0. So this all comes with the data. So solving a problem, what kind of models have recently been applied? A lot of advancements have been made actually in this year, working with the same kind of data set. What has been just applied is, for example, XGBoost regression model, which below we see a figure. The paper is also accessible with a link below, and I can send it to you guys to have a better look at it. But what is amazing about this one compared to 2014 is that it actually could depict more smaller damage, so the 15 centimeter damage that was before impossible from the same data set, which means that a lot of unknown things and also the quality of the data can yet be improved. And also an ANN method has been applied, coming to different results. And what is here done is it's another way to determine the damage sensitive features. I'm not into the details of these machine learning algorithms, but to add on what I just said, even more advancement in October 2021. So what kind of models would be interesting for these channels? So I made a list together with Sako of potential avenues to pursue. And here are a few of them: random forests or RNNs. I think if this is something you would like to do, we can go into more detail when we form the groups of the challenge, of course. But these are the directions we were thinking of. And what steps are needed to reach the goal? So what is really important is to separate the influence of all these environmental and operation conditions, because they have a high impact on the quality of the results. They have like a 5 to 10% influence on the vibrational data. But also what now limits the industry to apply this is the transparency in machine learning techniques. So increasing the transparency on what comes out of it and what we can distinguish in the data without being a data scientist as well comes to value into making this a solution that can be ready to implement on actual wind turbines. But also we have now one big data set that's from one single wind turbine. And as you may have already known, you don't want bias in your data set. And especially for this one, this is now a very old wind turbine. So we have to look on a way to make this data set more applicable to modern wind turbines as well. And what are sub-goals contributing to this goal? That's pre-processing all this data. We have to look how to increase the quality of the data that we have here, and also implement different feature engineering techniques. That will be a separate group, and then eventually look at the possibilities for even better advanced models to even increase the progress that has been made past October to an even higher level. So what are the masterclasses? I'm going to actually start with the domain expert because that one is confirmed and just today. So I'm really glad to share that with you guys. It's the creator of the data set that we have from the Vestas V27. He will give a masterclass in vibration analysis. And then the person who is more the tech expert, she is actually the leading the project for the lab environment test that you will start with dataset A. And we are trying to get her into a workshop to get you guys introduced on where she's working with currently, how our progress is, and what advice she can give you guys.
I did see one question in the beginning about when the blades of the windmills are checked. They need to be stationary, right?
Yes, they're working on it. Say if someone needs to crawl into the blades, yes, they need to. The whole wind turbine needs to be stand still. What they are looking at is, say, if they can take with drones, if they can take pictures, and also there will be an AI challenge of distinguishing, say, the pictures that are taken by the drones and to see what damage is on the outside of the blade, but then you still can't really see in the blade. So that covers only part of the problem.
And so with this new technique, we don't need to stop the turbines anymore, or do we?
No, it's that's the whole idea. It's say 365 days per year. You can monitor the wind turbines. You don't have to stop them, and which is specifically important for offshore because there is much more wind. Nobody wants to have really too many of the turbines in the backyard, so more and more of them are moving offshore, and there you want. Let's say also there is more wind, so with drones it becomes more complex to watch even the outside of the blades. So yeah, if you ask the experts and say how are you going to monitor those wind turbines, say 10 years from now, they don't really know.
Magnifying the importance of what we're doing, I guess. That's great.
What is actually the expected difference between the smaller blades and the larger blades? How do you expect that to influence the data? Like now we're looking at the shorter, older blades, but as you mentioned, the current ones are around 100 meters.
Mm-hmm. Yeah, so there are multiple ways it affects the data. Okay, so first one, the older wind turbines of this data set that are way more stiffer are also more robust. So you don't see damage occurring that because it's artificially induced. Don't see damage in these types of wind turbines that often. And how I would see this in the data is that if you have a longer blade, you reduce the stiffness. So I assume for this that a lot more vibration is measurable. So when damage is actually in a blade with a higher diameter, I think this will affect more the modal shapes.
And do you know, is there something changed about the materials, or are the materials, have they stayed the same over those years?
Yeah, so to increase the size of those blades, you have to reduce the mass of the blades. This is why you have this complex aeroelasticity in these blades, because to have a 100-meter blade, you cannot have the same mass. You can only try to design it with as light as possible. So also more flexibility gets into the blades.
Yeah, so just from my non-technical point of view, my understanding was that, say, when the blades are becoming longer, that the natural frequencies become lower on one end. And as Jesse said, there will be much more other movements in that blade. Let's say the shorter blades are stiffer than the longer blades. The tip speeds will be higher, of course, with longer blades. And as Jesse said earlier, the materials, the design of the blades, and that's the trade-off that the blade designers have. Say, how can we make with, of course, a longer blade will have more material than a shorter blade, but per meter, say you want to have less material because you want to make lighter blades per meter blade, say.
Yeah, but the material type is the same. So it will all be, I guess, just stainless steel, like, or do they
No,
use...
no. It's composites materials. So it's not. It's how do you call it?
Yeah, it's composite materials. It's like the same if you design a wing of an airplane. That's not from stainless steel either. It has to be really light and really stiff.
I have one more question. If there are already any ideas about reducing the noise within the recordings.
Yes. So reducing the noise in the recordings. Yeah. So what I saw is that the last advancement, but I could be wrong here, so excuse me if I'm wrong, but there has been looked at the total amount of runs, and then there's been looked at temperature data, and it has been noted that at some point there were extreme weather events. So getting these extreme weather events or anomalies out of your total amount of runs increased the how do you say it? Accuracy. Yeah, indeed. So you have to really work with the data and see, okay, do I also see some outliers in the amount of runs that can I correlate to metadata, the metadata that's accompanying to predict? And perhaps this is not a good representation of a normal operating wind turbines, but start with normal weather events. So
yeah, that probably makes a lot of sense to keep out the extreme weather events first. And I think that it makes a lot of sense to also try and at least factor in the temperature, because you want if the temperature and other weather data, because you want the model to be able to predict that basically, such that it can filter that part of the data to be able to also predict the actual damage, because otherwise it will be probably very distracted about those changes in the data, and you want it to focus, of course, on the damage. But one way of doing that is to actually also make it predict temperatures and all the other environmental data, so that can focus on those via other parts of the model, and then are left with the features that actually determine damage.